Selection of gems. In this section, we will learn about the physical properties on the basis of which we select gemstones. Criteria of selecting gems. The main criteria for the choice of gemstone is its color. The quality or value of gemstone depends on the following factors. First, play of color. Then, chatoyancy, luster, its optical properties, and the cut. The beauty is a function of its degree of refraction and color, its fire or display of prismatic colors, diachronic ability to display two different colors when viewed in different directions, and transparency. The choice of gemstones will be based on its inherent nature. Diamonds are valued for their fire and brilliancy. Ruby or emerald must have a high intensity and uniform color. Star sapphire and star rubies are chosen on the basis of star effect, called asterism, beside their color. Now we will study each of these properties one by one. First is play of color. It is a phenomena used by irregularities and miniature cracks inside the stone. Under observation, certain areas or pockets of stone tend to exhibit brilliant areas of color that changes in hue and size as the stone is moved. For astrological purposes, this is considered as defect and such gemstones should be rejected. Next is chatoyancy. It is the optical property of irregular interior reflection due to fibrous structure of some gemstones. They appear as ridge of eye that tends to rotate like an eyeball as a stone is moved. The intensity of the fiber increases the prominence of the ridge or eye. This feature is seen in tiger's eye or cat's eye and is a prized quality of the stone. Next is luster. In the mineral world, luster comes in two main types, non-metallic luster and metallic luster. In addition, an intermediate type, submetallic, is sometimes used as description. However, the gem industry most commonly deals with the non-metallic varieties. Most gems don't meet the criteria for metallic or submetallic luster. Now you will learn about the type of luster. The first type is adamantine. This term describes gems with a brilliant, mirror-like appearance, just like diamonds. Second is vitreous. Most gemstones, including popular jewelry species like quartz, topaz, tourmaline, have a shiny, glass-like luster. In some reference works, you may encounter glassy as another term for this type of luster. Next is pearly. Gems with this type of luster have surfaces that looks like that of pearls. Some may even show iridescent colors on their surface, like the orient of pearl. Gypsum and charoite may show pearly luster. Next is silky. Some gems, like ulexite, shows fine pallor threads that looks like the texture of fabric. This is known as silky luster. Greasy. Gems with a greasy luster seem to have a layer of oil or a fat on their surface. Example of this luster include graphite and green serpentine. Waxy. Gems that may show this luster, like turquoise, opal, appear to have a layer of wax on their surface. Then resinous. Amber consists literally of preserved prehistoric plant resin. Therefore, it should come as no surprise that this gem material has a resinous luster. Fluorite gems may have a resinous luster too. The next is dull. A dull luster simply means the gemstone reflects little light, such as rhodonite or kaolinite. The last type is metallic. Metallic luster, a reflective metal like appearance, is a term not used for gemstones. Hematite, however, is a notable exception. It has a striking metallic sheen, and gem cutters have carved cameos and made beads from this material. Now you will learn about the optical properties. A gemstone's optical properties are very sensitive to minute changes in composition and strain within their crystal structure. Therefore, accurately measuring them is very useful for identifying and distinguishing one gem species or variety from another. The first is wavelength of light and gemstone optics. Light travels in the form of waves, like ripple on a pond. This forms the basis of crystal and gemstone optics. To put this in familiar terms, different wavelengths are different colors and the amplitude is the light's intensity. Light vibrates at right angle to its direction of motion and the vibration takes place in all directions perpendicular to the light path. Second is refractive index. When light passes from one medium, such as air, into another, such as water, it slows down. In addition, the light path bends. The deviation always refers to a line perpendicular to the interface between the two media, known as normal to the interface. The light always bends towards the normal in the medium in which the light travels slower. Now, critical angle. Light traveling from a given medium into a less dense medium, for example, from a crystal into air, may strike the interface at such an angle that at that interface the light totally reflects back into the denser medium. The incidence angle at which this takes place is known as the critical angle. This angle has great significance for gem cutting. If a faceter cuts a gemstone at angles matched incorrectly to its refractive index, light entering the stone may leak out. The bottom, this causes a loss of brilliance. However, if the angles are correct at the bottom of the stone, light is totally reflected internally and returns to the eye of the viewer. This creates most pleasing brilliance. In fact, gem cutters facet stones precisely to create this wonderful return of light. Now, isotropic crystals. The crystallographic symmetries of gemstones determine their optical properties. For example, isometric crystals have crystal structures highly symmetrical in all directions. As a result of this symmetry, light traveling in any direction within an isotropic crystal travels at same speed. Within the material, no single direction measurably slows down light. This is also true of amorphous materials such as glass, which have no crystal structure. Such materials are called isotropic and are characterized by a single refractive index. Anisotropic crystals. In all other non-isotropic crystals, light separates into two components, that is, polarized rays known as the ordinary ray and the extraordinary ray. All non-isometric crystals cause this splitting of incident light and are called anisotropic.